teaching and research. He graduated in mechanical engineering from Anna University, Tamil Nadu, 2006. Joined Paracord Product Private Limited post in the same. Subsequently, he completed his ME from Madras Institute of Technology, Chennai in 2009. His PhD from IIT Madras in 2018. His PhD thesis is based on laser surface texturing on piston rings to improve its tribiological characteristics. He has published 8 research papers in refereed international journals and presented 8 research papers in international conferences. He secured the Institute Research Award from IIT Madras in July 2018 for his contribution towards the quantity of the research work during his research. His research interests are metal additive manufacturing, extension of nanosecond laser ablation, femtosecond laser machining, laser surface texturing, tribiology internal combustion engine, surface engineering biomedical implant, and modeling of fluid flow. Now, I am delighted to invite him to enlighten us about the strategic challenges and barriers ahead of additive manufacturing. We welcome you, sir.
Thank you.
So you can take over the session, sir.
Okay. Please confirm the visibility of the slides. It's visible.
Okay, sir. Okay. Can you share the screen, sir?
Yes, I have shared the screen. Are my slides moving? Please check whether the please check whether the slides are changing.
Sir, we could not see your slide. So 1 minute, sir. 1 minute. So please try now, sir.
Same issue. No? The share that icon is visible. I share the window, the tab, PPT alone.
Okay, sir, you can share it, tab, sir.
Okay. Are you able to see the slide?
Yes, sir.
Yes, sir.
Okay, I'm changing the slide. Is it changing? Are the slides changing?
Sir, no, sir, the slides are not changing, sir.
I have to share the entire screen. Yeah, now it is. I hope you are seeing the slides now.
Yes, sir.
Okay. So my presentation is about strategic challenges and barriers ahead of additive manufacturing. I'm Dr. Adil Maran. And the contents of the presentation I plan to give today is government policies in additive manufacturing and various companies that are manufacturing additive manufacturing machines, and some companies who are closely related to additive manufacturing. And the challenges. This is the main content of today's presentation. Challenges in various aspects, such as design challenges, technical challenges, additive manufacturing suppliers, and then I will summarize the entire presentation. So this is the slide. So why 3D printing is essential for any government? For India is boosting the role of additive manufacturing in many sectors. Why Indian government requires 3D printing policy? Yes, they have established a policy, 3D printing policy. What is the need? Because they understand that the next 50 to 100 years, so this field is going to dominate in manufacturing sectors. So conventional manufacturing on one side, it is very well developed by government. We are way ahead of many countries in conventional manufacturing sectors. But this is the latest trend and latest trend in manufacturing, which is additive manufacturing. Why government is sticking to these policies, and what is this policy is going to award for Indian citizens? You can look at the slide. The aim is to develop 50 India specific technologies for materials, machines, and software. 100 new startups are about to come, which is related to additive manufacturing. 500 new products, and train at least 1 lakh new skilled workers. This is the aim for Indian government for the next coming years. And also they plan to increase the India share in additive manufacturing sectors by around 5% of the global additive manufacturing market. And the target to add $1 billion to national GDP by 2025. This is the government policy. But I read the newspaper about these kind of policies. But what is pulling back while establishing these kind of policies? There are a lot of limitations, challenges need to be overcome with respect to additive manufacturing, like lack of standards, lack of quality issues, hesitation in adopting this additive manufacturing in the manufacturing sectors, and the government is also fearing about the risk of job losses, because conventional manufacturing, if you manufacture a complex part, the conventional manufacturing certainly will give jobs for a lot of people. As you see in the mass production industry, a lot of people are getting work. But in additive manufacturing, it's just a one machine which give you a complex product, a complex shape product. And also the government is fearing about high costing of the machine. At present, the costing of that machine is very, very high, because any new technology, if it is introduced into the market, initially the cost will be very gradually over a period of time, with more and more number of users use the particular technology, the cost will eventually reduce. That is the government aim for the next coming 10 to 20 years. They plan to boost the sector, additive manufacturing sector, by implementing all those things. And also I read one more news recently. Additive manufacturing tech expo to be held in Hyderabad on December 2 to 3rd. So earlier, 10 years before, we haven't come across this kind of additive manufacturing informations, because that was the time when additive manufacturing process slowly, eventually it was evolved. Now more and more number of people are talking about additive manufacturing. Even a person who is not in the domain of mechanical engineering, they very well know about additive manufacturing in the recent days. We are seeing that. So that is the kind of awareness that additive manufacturing is established. And about the Tamil Nadu government, what they are planning to contribute for additive manufacturing is, they already set up infrastructure for Industry 4.0. They plan to around rupees 75,000 crore investment in aerospace and defense. They have tie up with General Electric India. They plan to develop various products with additive manufacturing. They have given a separate space in Tidal Park, and that was inaugurated by our Chief Minister. I come across this news also. So what are the various additive manufacturing companies in India? These are some of the companies that naturally works in additive manufacturing: Atlas Copco, Prestige, and Daimler, Wipro 3D, and Faber. There are many young startup companies also. They are making products by using 3D printing. So 3D printing is not about producing a product with polymer. There are many more than that. Not only polymers, metals, alloys, ceramics, refractory materials. So many materials can be made by many different additive manufacturing technologies. And these are the top startup additive companies in India. Okay, if you Google it, you can see their web pages. So Brahma, 3L machines, Hyperdent, and so on. So there are a lot of startup companies, young companies, youngsters, a lot of business people who are wanting to take that to manufacturing to the next level. They start a company, they develop the company, and they are earning profits. And the latest news, day before yesterday, I went across the streets. Chennai headquartered Agnikul Cosmos. They successfully test a 3D printed rocket engine. It is a single part which is made of a material called alloy, nickel alloy. I think it's inconel. It is made up of a single. It is made as a single piece. They have tested a 3D printed rocket engine in ISRO headquarters. So they have some tie-up. So the name of the engine is Agni Lead. Okay, the Agnikul is the name of the company. They developed an engine called Agni Lead rocket engine, a semi-cryogenic engine. It's a mixture of it uses a mixture of liquid kerosene at room temperature and super cold liquid oxygen. Well, it has certain payload also. It can lift up to around 300 kg. This is the Agni Lead rocket engine. It is made of Inconel 1718 alloy. It is a single piece engine developed by that IIT Madras research park startup company Agni. So that Agnikul company, they have raised a total funding of around 35 million dollars, US dollars, from various agencies. Specifically, Anand Mahindra of Mahindra and Mahindra, he has also given some funding to develop such rocket engine, single piece rocket engine. So similarly, similar to this single startup, like Agnikul, many such startup companies are coming forward to develop a product specifically by using additive manufacturing process. Around this 53 space tech startups in India have collectively raised funding of rupees $220 million. Because if any one person talk about additive and he uh, uh, I mean, he try to invest. He try to build something by using additive manufacturing. So many investors are coming forward to support in terms of monetary support or else like ethical support, whatever it is. Many companies are now giving money to get a better product, complex shaped product in additive manufacturing. That is the, encouragement. So key goals of India's 3D printing policy is to establish India as a global hub for additive manufacturing, to develop and safeguard India's additive manufacturing intellectual property. And many people are fearing about adopting this additive manufacturing technology for the current scenario, citing that getting a profit in additive manufacturing is difficult, but government is encouraging. They are giving a lot of inputs apart from giving monetary support and encouraging. They are also the India's 3D printing policy. The fourth point is enhancing manufacturing capabilities and encouraging foreign technology manufacturing in India, and encouraging and incentivizing indigenous manufacturers. So already, so many companies are way ahead of India in additive manufacturing. For example, US, France, Japan, Germany, already they are way ahead. They are making additive manufacturing machines. They are creating a lot of additive manufacturing products made by metals, ceramics. But India is slowly became the gaining the momentum now, and certainly in another 10 years, we are on par in developing manufacturing products by using additive manufacturing. So these are the 7 popular additive manufacturing process used for making polymers, metals, ceramics, refractory metals. I specifically going to focus only on 2 processes. One is powder bed fusion, other one is directed energy deposition. So these 2 processes are used to making. Sorry, I'm getting some message. I'm not able to see the message. What exactly it is? Okay. I'm going to specifically, I'm going to discuss about two specific processes. This is called powder bed fusion process and directed energy deposition process. These two processes are very, very popular for making metallic products. So apart from these two processes, there are various other processes which is very, very useful for making metals. So the binder jetting is all just also used to make metals. Binder jetting, but it is not covered in this topic. That for photopolymerization, it is used to make plastic parts. Similarly, FDM, it is also used to make plastic parts. That process is not covered in this topic. So for making metals, primarily two processes are very popular. As I said, powder bed fusion process and directed energy deposition process. Within powder bed fusion process, there are a lot of types, which is called selective laser sintering, SLS. We call SLS. And selective laser melting, direct metal laser sintering, and the second is electron beam source. The first three topics, SLS, SLM, and TMLS, utilizes laser source in the part. And the second one is electron beam source. You can use electron beam to melt metallic powders. So this process is suitable only for electrically conducting metals. So this selective laser sintering was introduced by University of Texas in Austin, USA. 1980s it was introduced. Gradually, many people started using. Then they got patent as well. So they switch over to some other process. The Fraunhofer Institute in Hague in Germany, 1995. Instead of using, because of this patent issue, they didn't use selective laser sintering. They invent a new technique which is called selective laser melting. But almost selective laser sintering and selective laser melting, both the process works the same mechanism. There's no drastic difference between SLS and SL. So selective laser sintering, SLS, is called SLS, do not fully melt the powder, but heat it to a point where the powder can fuse to it. Only the outermost that layer of the powder will be melted, and the two powder particles will be fused together at a molecular level. So that is called selective laser sintering. And selective laser melting, the powders will be melted fully. So normally the laser energy is very high, so as to take that powder to melting point, and the fusion of two that powder particles is possible. So full melting is possible in selective laser melting. But generally speaking, all the powders will undergo melting. Even if you use SLS and even if you say selective laser sintering, there are also most of the time powder will melt. Sometimes some materials cannot be processed in normal atmosphere, working atmosphere. So you have to give a separate working ambience. Just you have to supply argon gas, or else you have to use a vacuum atmosphere for certain materials if you want to stop the reactivity of the metallic powder with outside ambience, atmospheric gases. So that is also there. And one more term which is called direct metal laser sintering. So this is similar to SLS and SLM. So this term was coined by EOS GmbH, a German additive manufacturing company. Instead of calling this additive manufacturing process as SLM or SLS, they coined a new term, DMLS, direct metal laser sintering. But generally, what is SLS and what is SLM? When to use SLS, when to use SLM, and when to use DMLS, if you ask me. If you are working with an alloy, some sort of alloy, you can call a process as SLS, okay, or a DMLS. If you are working with pure metal, such as titanium or pure nickel, you have to use that SLM, selective laser melting. Most of the time, we work with an alloy, isn't it? If you work with the titanium, you are working with Ti64. If you want to work with nickel, you have to use Inconel 718 material. This kind of materials are there are alloys. So majority of the time we use SLS instead of SL. Selective laser sintering is widely accepted term. So the challenges in additive manufacturing, there are a lot of challenges: technical capability, financial, design, IT integration. There are a lot of challenges in establishing additive manufacturing in the global market. So almost all the companies are facing these challenges. So I will explain challenges related to technical and financial design. So this capability and IT integration, that topic is not covered in this presentation. So what is the difference between powder bed fusion and directed energy deposition process? This is the animated file. You can see the animated file. The first picture is powder bed fusion process. So selective laser sintering, selective laser melting, DMLS all comes under powder bed fusion. The first picture is powder bed fusion process. So there is a bed which contains a powder, metallic powder. There's a bed which contains metallic powder. So inside the bed there is a base plate. So over the plate, the powder is selectively fused by using laser, or it may be electron beam source also. So once the layer is coated, the powder bed is dropped down by one layer. The next layer is coated over the previously formed part surface by means of recoater plates, and a fresh layer is again fused by means of laser or electron. This is called powder bed fusion process. The second picture you can see directed energy deposition process. So here there is no such powder bed. The source is traveling. The source is not kept in a constant position. The laser source is moving. So along with the laser source, you need some feedstock material sintered to coat or to deposit a layer. The feedstock in DED, it may be powder, it may be wire. So in both the forms, the feedstock material is available. So inside the nozzle, the feedstock wire or powder will be traveling along with the laser, and the laser will meet this powder at certain spot in between the material that is deposited and the laser nozzle. So laser melt the powder, and the molten material will be traveling, and it is deposited on this layer, layer by layer fashion. So we can call it as a traveling molten pool. So DED and powder bed fusion process both are entirely different process, even though both utilizes laser. The way in which the material is deposited is different. Here the powder is kept in a bed. Here the powder is traveling along with the laser. So the process is little bit different. And what is the major difference between these two processes? In powder bed fusion process, the size of the product will be restricted. So the size of the product depends upon the size of the chamber. Am I audible now?
Sir, yes, sir.
The size of the part in which you are building depends upon the size of the chamber. The chamber size may not be so big to make a big size product. So the powder bed fusion process, the first limitations in terms of part size. So we have limited part size in case of powder bed fusion process. But in directed energy deposition process, there is no such limitations. You can make a very big product in short duration of time. Deposition rate is very, very high in directed energy deposition process. Simply saying the directed energy deposition is primarily used to make a repair work. Suppose if in a gear, in a spur gear, if one or two teeth are broken, you can deposit that broken teeth. Instead of broken teeth, you can deposit fresh material, and you can make it up as a new gear without any major. Fresh gear. You can make it as a fresh gear instead of replacing it with another gear. You can make a teeth by using a directed energy deposition process. That is the advantage of DED. But DED has a lot of disadvantages as well in terms of accuracies. The product made by DED may not be accurate. Design inaccuracies. That is the term used. say about the limitation in the design inaccuracy, and also part strength may not be very high like that of SL. So design challenges, there are three design challenges. One is anisotropy, hole thickness, and print orientation. These are the design challenges. And technical challenges I'm going to cover in this presentation is challenges associated with powder, material associated with material defects, challenges associated with support structure, associated with surface quality, etc. may become. So what is anisotropy? So look at the picture. So there are two parts printed in a different orientation. So the first part, cylindrical part, hollow cylinder, it is printed in a vertical fashion, and second part is printed in horizontal fashion. So which one is preferable? Both these parts will be anisotropic. Anisotropic is the properties will be different in different directions. So in the first part, the printed part, which is vertical, which is kept vertical, the strength is very less in the direction of in the Z direction. In the Z direction, if you apply load, the part will very easy because it is this is the layer by layer deposition process. If the layer to layer strength is very less in the Y direction, if you apply inputs, that part will fail. But if you more focus on your aesthetic look of the product, the first part is pretty much good. It looks very good, isn't it? So that is required. So if you don't worry about the strength, the first picture, which is printed vertically, that is the correct option. That's the correct way to print. The second picture, the object, the hollow, the same hollow cylinder is printed horizontally. So here, it can withstand the load if the load is applied along the axis of the hole. It can withstand because the layers are printed in a direction perpendicular to the load acting direction. So that way, so this printed, the horizontally printed object certainly will have huge strength when compared to the first part. But there are a lot of limitations while printing the part such as this one, which is printed horizontally, because we need support structures to build this part, because most of the parts are overhanging. The parts are overhanging. So inside the whole inner surfaces cannot be printed as it is. They cannot be printed so much easily. You need support structures to print the whole. A lot of structures are overhanging. So printing is difficult in second case. So in both the cases, the parts printed are not anisotropic. They are all not isotropic. Both are anisotropic. Strength is not uniform in all the directions. So that is the point. So proper orientation is essential for printing a product. Whether you want aesthetic look, or if you want a strength, or if you want to minimize the support structure, etc., you have to. These are the parameters which it decides which orientation is suitable for printing. Look at the picture. Which is the best way to print using UTM, universal testing machine? So they have to go with the shape. So after printing the shape, to use UTM machine to test the tensile strength, which is the proper orientation. The object is kept at 0 degree, 30, 45, 60, 90. So again, the printing direction depends upon the load acting. If you print an object at 0 and the load acting direction is vertical, that is a bad idea. You should not do that. Okay. And the object which is kept flat, 90 degree. So that is the best way to print if the load acting direction is along the axis of the this material, standards specific. Okay, if you have to print it by keeping the object lying down. That's the best way to print. If you print at 60 degree, 45 degree, and 30 degree, you need support structures, lot of support structure, so under Z directions. And second object is printed in XY direction. So the force acting direction is horizontal. So what is the best way to print? Whether the first one, you go with the first one or second one? Obviously, the second one will withstand. The first one Certainly, it will not withstand the large amount of load. Challenge for any manufacturer is the minimum size of board that can be made on a material. You can make a small board. Say, for example, 100 micron small board is possible by using a smaller drill bits. The 100 micron drill bits are available in the market. You can make a small hole or small slot with the size of 100 micron. It is possible. Even 15 micron is also possible. But manufacturing machine, that's a little challenge. The smallest hole that can be made by additive manufacturing depends upon the thickness of the material. Okay, the first picture, the thickness is 2 mm. Thickness of the material is 2 mm. So in that material, you are going to make slots. But the second part, thickness of the material is 4 mm. Slots are made gradually 6, 8, and 10 mm. These are the thickness 2, 4, 6, 8, 10 are the thickness of the material. So over that material, some slots are made. Okay. Then come to the first one, second 2 mm thickness. So almost all the 5 slots are clearly visible, isn't it? So that you are going to make in any material depends upon the thickness of the material. Might very make small features. Print orientation. So look at the picture print. Whether you print the chair shown in the website, or will you print the chair in the right side figure shown in the right side figure? Which way is the best? Which is the best way to
Right
print?
side figure, sir.
The right side. Why?
Because we can avoid the support structures, sir. While we have gone for first one means we need to go for support structures, so there will be a lot of losses while gone
Yes,
for this.
absolutely. That's the correct answer. In the first picture, you need a lot of support structure. That is overhanging shape, isn't it? The second picture, there's no need for support structure. But there is one more problem in the second picture. Will you remove the part from the build plate? So you have to cut it. You have to cut by using some other process, isn't it? How will you remove it? You have to use wire EDM or some other process. So that removal is a little bit difficult. From the build plate, you have to remove the part. That is difficult. So you have to keep it in that way. So what are the challenges associated with the powder? So when you think of any project in additive manufacturing process, this is the first step for any manufacturer, for any business person, for any academician. So they have to buy the powders. Okay, metallic powder. If you want to use plastic, you have to purchase plastic powder. You have to form pellets. But for any manufacturer, they have to start with this kind of powders. The quality of the part depends upon the powders, quality of the powders in which you are purchasing. So what are the issues with powder handling? So there are a lot of issues. Reactivity, flowability issues, airborne particles, agglomeration of the powder. These are the main issues while purchasing the powder. Some powders are very highly reactive. For example, magnesium is very highly reactive in powder form. Even if it is exposed to atmospheric environment of magnesium powder, it will be reactive. That's a danger of fire hazard. And aluminum powder is highly reactive. So some powders are highly reactive in nature. Second one is flowability issue. So when you purchase the powder, so what is the shape of the powder in which you're looking for? You have to purchase a spherical shape powder, isn't it? So already previous lectures, I think they have handled this kind of problems. I assume that. So flowability issue is because of the shape of the powder. If the shape of the powder is perfectly spherical, the flowability issue is minimal. The powder has to flow, isn't it? In the animated file, you can see the slide arm moves the powder here and there. So the powder has to flow, isn't it? Then only you can make a smooth, finally you can get a good product. But if the shape of the powder is not spherical, if it is some other flat shapes, or if it is some other shape, sharp, if it is like a sharp object, then the flowability issue may come. So you have to keep it in that mind. You have to, when purchasing itself, you have to verify whether the powder is of spherical shape. Airborne particles. Okay, where some other particles are there or not. You have to verify. Agglomeration of the powder. Because of the humidity issue, you have to keep that powder. If you keep that powder for a long period of time in a room, it will acquire atmospheric humidity and it will agglomerate. So that problem should not happen. You have to keep it in a very safe environment. So the ultimate point is how to purchase powders from reliable supplier, quality supplier. Simply because of economical reasons, if you purchase powder from a supplier, is not very genuine, you will end up in a spherical powder. So there are a lot of ways to make powder, automation process and mechanical crushing, chemical reduction. These are the process that that make powders. So popular processes, automation. There are various processes: water automation, gas automation, etc. are available. So gas powders, water suitable for material which is very much affinity towards water. So most of the time, gas automation is recommended. And after purchasing the powder, if you look that powder into thing, so you micro sizes, uniform spherical shaped powder with different ranges of sizes. The spherical shaped product, smaller size particle will occupy space or gap between the bigger size particles. So that way, the density of the product will be very good. Porosity will be minimized. Okay, that is also an aspect while purchasing the powder. So irregular powder shape, such as elongated particles, should be avoided. You have to carefully look upon it that irregular powder particles are present or not. You have to verify that. Satellites are agglomeration of small powder particles. That should be avoided. The powder particle should not contain any satellites. If it contains satellites, what is the problem? So in the picture, you can see small satellites. Satellites means the agglomeration of powder. That's called satellites. If your powder particles contains a lot of such satellites, the recoater blade will find it difficult to move the powder from one area to other area. So you have to supply more amount of energy. The flowability issues will come. The powder coating may not be uniform. That's the problem. Then hollow powder particles is not recommended for sure because it has high fire hazard. Hollow powder particles, but also it affects the density. Affects the density by inducing unnecessary porosity in your final part. So you have to keep in mind all those aspects while purchasing the powder. So no need to purchase a bulk powder. Instead of purchasing bulk powder, you try some samples, you purchase some samples, test it in your lab. If you are satisfied with that, you can purchase in bulk. So I said there is a powder size distribution. Generally, the powder size will be less than 100 micrometer, which is recommended so as to improve the density of the part. More the powder size means it is not generally recommended. The powder size should not be more than your thickness of the layer. That is a general rule. So this is the layer by layer additive manufacturing process. So your powder size should be lesser than your layer thickness. Suppose if you are making 100 micrometer thickness layer, your powder size should be at least 1/3 of the layer thickness. You can purchase a powder size of 30 micron to 40 micron. That is good enough. So there are other powder considerations also. Because in powder bed fusion process is not an economical process. Because you make some products, you have to reuse the powders again and again. You have to reuse it. to prevent wastages. So if you are reusing again and again, the powder quality at some point of time will not be good. It will acquire atmospheric oxygen again. There will be some other issues will arise because of again and again recycling. So these are the summary or the overall view about powder handling challenges. So your system, that additive manufacturing machines will have sufficient powder reservoir. I mean, the size of the reservoir should be big enough to hold all the powder to get a sufficient amount of products. The second one is proper transportation of your powder to the build platform is essential. Third one is the powder must be spread to form a smooth, thin, repeatable layer of powder. And fourth one, the powder spreading must not create excessive shear force. Why? Because excessive shear force will disturb the already formed layers. Okay, the powder spreading must be very, very smooth. So here you can see two pictures. The first picture, which is called Doctor Blade. That part is called the Doctor Blade. It distributes the powder. Even though it distributes the powder uniformly, the Doctor Blade is not used. The Doctor Blade is replaced by a roller. Because Doctor's Blade, many manufacturers felt that the distribution of the powder was not uniform. And also it creates unnecessary shear forces on the already formed layer. So the Doctor's Blade is completely replaced by a roller. So this spherical roller will rotate in opposite direction of the direction of the feed. So it distributes the layer very uniformly. So that is why the second picture is widely used. So there are small things manufacturers are focusing to improve the quality of the product. One such small thing is this: instead of Doctor's Blade, rollers are used to distribute the layers. And one more thing, the powder size should be very, very small. For any additive manufacturing process to be successful, the powder size should be small. That is a requirement. The lesser the powder size, the density will be more. Lesser the powder size, lesser the porosity. Okay, the powder size has a close relevance with all those quality terms. But where the issues come is reactivity. Small powder size are more reactive. As I said, magnesium is highly reactive. PM is highly reactive. You can't go for smaller size powders. There are many other issues with the smaller size powder. Even though it is very beneficial to make a final product, there are many other issues with the decreased powder size. Also, with the or any other electron beam is falling on the powder bed, what will happen? The powder will splash. So it will stick to the adjoining areas slowly. It will stick to the optics also. There are many optics used in laser. It will stick to the optics because laser has to be focused. For focusing the laser, you need some optics. So it will stick to the optics. It will stick to the nearby areas. And sometimes it will deflect the laser beams also. Okay, this kind of quality issues come when you use lesser powder size particle. But there are other advantages as well when you use decreased powder size, like better surface finish, high accuracy, and thinner parts. So you have to decide which powder particles you have to use and what are the issues you have to decide. As a manufacturer, you have to decide. So the recommended powder size for powder bed fusion, PBF stands for powder bed fusion technology, ranges from 20 to 40 micrometer, whereas DED 45 to 150 micrometer. This is the recommended size. Even if you go for recycling, as I said, recycling is a good idea, of course, but you have to take some precautionary steps while handling powders. It will easily mix with atmospheric oxygen, acquire oxygen. So again and again, if you recycle, more oxygen content will be added in the powder. So that will reduce your quality of the product. So here one statistics. recycled powder after 21 times. So initially, virgin powder contains 0.08% oxygen content. Recycled powder after 21 times, the oxygen content has increased to 0.19%. That is the issue. So you can't use the powder again and again. There are other challenges. This is a very interesting thing. There are a lot of other defects rather than challenges. These are the defects associated with the material. Okay, porosity is a defect. Residual stress, heat affected June, cracking, part growth, and isotope fusion process and so directed energy deposition. Both are all thermal process. So obviously, these kind of process are expected, but how to reduce the porosity? That is the question. Porosity means the part produced after 3D printing contains a lot of holes inside it. So it reduces the density and it reduces the strength. So we have to minimize the porosity. So these are all not organized porosity. These are all unorganized porosity. For some applications, porosity are required. For biomedical applications, porous structure is required. But this porosity is not organized, unorganized. So fracture or failure may happen at any point of time on any direction because of this porosity. So we have to eliminate that porosity. And this residual stress, because as I said, it is a thermal process. Because of thermal history within the material, difference in expansion and cooling of the material during laser material interaction. This kind of the residual stresses are happening. We have to eliminate that. We'll see how to reduce residual stress by different ways. And heat affected zone. That is also one defect. Heat affected zone is a portion of the material just not melted, but that microstructure of that place is changed due to intense heating. Because of the heating alone, nearby laser deposition area, the microstructure will be changed. The microstructure, it may be increasing or decreasing, but the size will be changed. Sometimes the microstructural change will end up in embrittlement. So that is the problem with the heat affected zone. And fourth one is cracking. Because of intense heat and residual stress, cracking may occur. Fifth one is part growth. Part will grow in size. I will explain what is meant by part growth later. So this is the layer centering versus melting. If it is centered, the part contains a lot of porosity, and if it is melted, there is no such porosity is visible. So melting is also a very good way to 3D print rather than centering. But for some applications, centering is the best. So this is the porous structure. I mean, unorganized porosity material due to thermal process. As I said, it is a rare bit of powder. So 100% product is not all possible by using additive manufacturing. That may not be 100% dense. Maybe 90% or 90% density can be attained even with the proper processing parameters. It can be attained. Otherwise, 100% density may not be attained or attained. So how to minimize the porosity? Of the part during printing, or if the product is printed, the part is, there are two ways to push. One is during printing, it is possible to minimize the porosity. The part is held at elevated temperature after scanning. That is the way to control porosity during processing. Carefully controlling the part by temperature, cooling rate, and other parameters. You have to carefully control all the parameters, laser related parameters to minimize the porosity. So there are a lot of laser parameters such as laser energy, laser energy density, scanning rate, laser scanning rate, and laser focusing that area, laser spot size. We call it as laser spot size. So all these things will affect the porosity. A part which contains more than 6% of the porosity, certainly the mechanical properties is not that good when compared to what we expected. The porosity of more than 6% of the product is generally not recommended. Mechanical properties certainly will be down. Mechanical properties refers to strength, mechanical strength, fatigue properties. Everything will be affected by means of this porous structure. Generally, the porosity should be kept minimum. And the second most important is residual stresses. Wait a minute, my slide is not changing. Okay, why residual stresses are formed in the material? Being a thermal process, and that to layer additive manufacturing process. When a new layer is deposited, what will happen? It tries to expand, and gradually that new layer will be cooled. So now one more fresh layer is again coated on the already formed layer, which is now contracting layer, because the previous layer is now getting cooled. It is now the size of the previously deposited layer is now reducing because of contraction. So over that contracted the layer, we are now depositing a fresh layer or layer of metal, one more layer. So because of this expansion and contraction, this fresh layer tries to expand, but the already formed layer behind it tries to contract. This difference in expansion and contraction will create residual stresses. Even though it is not possible to avoid it 100%, it is possible to minimize the residual stresses by some suitable ways. So, what are the ways? Let's see the ways to minimize the residual stresses. Generally, a part has tensile residual stress on the outermost layer and compressive residual stress on the inner layer. So, this compressive residual stress is almost always it is helpful. This compressive residual stresses increase the fatigue life of the component. But the tensile residual stresses, which is formed on the surface of any printed component, is detrimental. It is not your fatigue life drastically will be down if it contains tensile residual stress on the surface, because all the cracks start from the surface and gradually it will penetrate inside the material. So we have to carefully look into this issue to minimize the tensile residual stress on the surface. So that residual stresses occurs from a variety of mechanisms, mainly because of temperature gradients, difference of temperature at different regions. This occurs, and there are many other hypotheses also. It is due to inelastic deformation, structural changes, the phase transformation, and heat from the laser, etc. There are many other reasons, but how to avoid it? There are many ways. During designing stage itself, we can reduce it. We have to design a product in such a way that the part should be avoided. So the part should contain uniform thickness. The part should not contain any masses. So if the part contains masses, the large chance for this thermal gradient. So that has to be avoided. So in the design stage itself, we have to avoid this kind of design related residual stress problem. And you can preheat the build plate to minimize the residual stress to a certain extent. You preheat the build plate. You have to heat the build plate over which we are going to form the product layer by layer. That build plate needs to be heated. Other ways, you can heat the overall build chamber to certain temperature. Say, for example, 500 degree or 600 degree. You have to heat that build chamber to minimize this kind of residual stress issues. This is the picture taken from the book. The first picture contains a lot of masses. The second picture, the masses is ready. All the masses are reduced. Thicknesses are uniform. So all the part thickness is uniform. So that way you can minimize the residual stress to a certain extent. This is one way to design a problem. Okay, always try to eliminate the uneven thickness. Eliminate the masses. Minimize the residual stresses. That is one way. And the second design is Wait a minute. Yes. Okay. The first two pictures you can see the masses are not evenly distributed. The second picture, to because it will gradually when the part is printed, shown in the first picture, it will get a lot of residual stresses. The second picture is somewhat recommended because the thickness of all the parts are uniform, all the shapes are uniform. There is no extra material, so you have to design accordingly. There is a design-wise idea. Image the residual stresses. Meander hatch pattern. The second one is stripe hatch pattern. The one is chessboard pattern. So there are a lot of present these patterns, but the third one, chessboard pattern, will predominantly improve the material strength by minimizing residual stresses. That chessboard hatch pattern is mostly recommended for any product manufactured by 3D printing. That is called small island of patterns. There are small island of patterns. Instead of going in as a single, instead of going in a single go, instead of printing in a single go, it is possible to print it in small islands like chessboard hatch pattern. That pattern will help you reduce the residual stresses. So there are a lot of other steps like bullet chamber preheating, base plate heating, laser pre scanning heating. I'll tell you what is meant by laser pre scanning heating. All these will help to minimize the residual stresses. So I hope you understand the importance of minimizing residual stresses, because residual stresses is detrimental for many strength related problems. It will create unnecessary strength related problems. It affects the fatigue life. Okay, if a part, if you make some part which is used for aerospace applications, that undergoes cyclic loading, and if you use the part which contains high residual stresses in that application, your part will fail before the part reaches the yield point. Okay, so you have to carefully minimize the residual stresses before using it for any applications. This laser related process contains phenomenally high residual stresses. So this is the third method to minimize residual stresses. Instead of heating the powder bed directly by using laser, before heating the powder by using laser pulses, you can heat it by using some other process. That's called preheating the laser bed. Okay, you have to preheat by using infrared lamp. Then your laser will heat the part. So part growth, what is part growth? I'll show you one picture. You can understand what is maybe part growth. So wait. Wait a minute.
Yes, sir.
The slide is not changing. Okay, no problem. I go to the next slide. So the part growth arises because of the main reason for part growth is when first on the powder bed, because the laser scanning is based upon the part you have designed by using CAD softwares, and you have converted that part into STL model, and that STL model is replicated as your final part. That is a process. But when the laser falls on the powder based on the STL model, the adjacent particles, which is adjacent to the boundary area of that part, will also getting fused, and it stick to the part. So that way, the part will grow in size because it acquires powder. The laser beam acquires powder from the adjacent regions, and that powder is melted, and again it stick to the part. So the part is somewhat bigger in size when compared to your actual CAD model or STL model. Somewhat it is bigger in size. So you can minimize that. Post-processing method you can go for. You have to go for machining to take it to the original shape, or else you can do some adjustments. You have to make the part very smaller to keeping in mind that the part will be bigger than your STL model. That way, it is beneficial. That's called path growth. So these are the issues. Uh, System is hanging. I don't know what to do. So there are many such issues like path growth. It is completed. Yes. So development of there are a lot of other challenges with material also. Normally, a development of alloy yearly takes place a decade. The material cannot be developed just like that because so much hard work is required to develop a material and give it to the market. So if you use plenty of materials like a Tice Expo, Inconel for turbine blade material, etc., but these materials are not developed in a single day. So over a period of time, these materials grow. So like that, additive manufacturing is a new method, isn't it? So you have to carefully examine all the parameters, laser parameters, material parameters, etc., to get a quality product, so that the end user will be satisfied with your product. You have to keep that in mind. So materials wise, there are a lot of discomfort for additive manufacturing. I'm going to explain one by one. Generally, I plan to speak problems associated with two materials. One is magnesium, and second one is tungsten. There are a lot of issues with other materials also. Nickel, titanium, stainless steel. So these are the materials that can be printed by using additive manufacturing machines. So I'm going to focus only on the issues with materials such as magnesium and tungsten. This is the challenges associated with support structure. I forgot to tell about this. So you have to remove the support structure. You have to incorporate a lot of support structure to make a overhanging part. They are making a monolithic parts, isn't it? So most of the overhanging parts require support structure. So unnecessary wastage of material. That is the thing here. And the problem with the laser Gaussian beam. So the laser beam, because laser is used to melt the materials. So is my slide visible to all of you? Is my slide visible to all of you? Can anyone please respond? Is the slide visible?
Sir, yes, sir.
Yes, sir, visible, sir.
So there is some issue with the laser beam also. Laser beam is Gaussian. What is meant by Gaussian? You can see a bell-shaped curve. That is called Gaussian. So when the laser beam falls on the material, the center part of the beam, which possesses maximum intensity, whereas the outside portion of the beam will not have that much intensity like that of the intensity in the center. So the middle part of the beam melting is more, but the extreme end of the beam melting is very less. That is the problem with the laser. So the extreme end part may not be completely melted. So heat affected zone will be formed on the extreme ends of the laser beam. So you have to use an approach while scanning the powder by using laser beam. You have to overlap the laser beam so as to minimize the heat affected zone. That approach is what used. So there are a lot of laser related parameters you have to keep it in mind, such as laser scan speed, laser energy, scan pattern, scan spacing. These all affects the powder, part, final part. When coming to the size of the product, so how much size can a part can be produced by using additive manufacturing? So it depends upon the manufacturer who build that machine. So the size of the printer, this is the RCAM's largest built volume. So the diameter is represents the diameter of 350 mm for height and 380 mm. So you can make a product 350 mm across 380 mm. And diameter is 350 mm and height is 380 mm. That's the maximum size you can make. And there is an issue with the ease of use. 3D printers still. So you have a graphical user interface for your laptop, isn't it? Very easily you can access all the softwares and Microsoft Word, Microsoft Excel. Easily you can access it for laptop. So the picture is shown. This is the picture of Microsoft driver home screen. But for 3D printing machine, you cannot get a easy access or easy user-friendly graphic user interface. That is also an issue. Still now, the 3D printer manufacturers are not able to develop user-friendly graphical user interface. That is also an issue. It seems that my slide has some issue. It's not changing. Shall I close the slides and come back again? Will I show it again?
Okay, sir.
Okay, sir.
We'll wait, sir. We'll all wait.
Okay. Now, are you seeing the slides?
Yes, sir.
Okay.
Visible, sir.
The other problems with the laser is with respect to the reflectivity of material powder. Most of the materials may not absorb the laser beam. Some materials may be highly reflective. For example, aluminum is highly reflective. Gold is reflective. So if the laser beam passes the material, it has to acquire the laser beam and it goes to potent state and again cool down to normal temperature. That's the phenomena we expect. But in realities, most of the laser beam sent to the powder will be reflected. And so if in that case, the particles may not be fused together. So again, that is a problem. So the problem with the powder. In this picture, you can see the material is printed by using various laser energies, 18.5 joule per mm cube and 22.2 joule per mm cube, 27.8 joule per mm cube. So like that, the laser energy is increasing. So what is happening in the material, inside the material is that at lesser energy density, at 18.5 joule per mm cube, you can see a lot of porosity inside the material. The material is not completely fused inside the material. The powder is not completely fused. They end up in porous structure. So that is not what I expected. So slowly, the energy is increasing. The porosity is reduced. At a high energy of 83.3 per mm cube, the porosity is completely eliminated. But it creates another issue. The surface is not smooth. The surface contains a lot of roughness. So the thing is, at lesser energy, the porosity is very high, but the surface is somewhat smoother. But if you increase the energy, slowly the porosity is reduced, but the surface is rough. So you have to keep it in mind. What is the appropriate energy you have to use? What is the requirement? So this is the relationship between laser parameters. If you use high laser power and if you use high bed temperature combination, you can reduce dense parts and part will grow. Poor recyclability of the powder, difficulty in cleaning parts. That is the thing. There are plus and minus. Dense parts, producing dense part is positive. At the same time, part growth, poor recyclability, difficulty in cleaning parts are negative side. If you use low laser power, low bed temperature combinations, you cannot get a dense part. You cannot get a dense part or structurally reproduced. At the same time, better dimensional accuracy is there. Tendency for layer delamination. Delamination means layer will peel off. Laser power and low part bed temperature combinations. Non-unification buildup of residual stress and darling of bonds. So these are the issues with the laser. So you have to carefully use all the laser parameters. So you have to use a design of experiments kind of thing for all the materials which you have to try. So far, some standard design of experiments are available only for limited materials. Say, for example, titanium material. People are trying. The last 10 years, people are trying. They are using some standard processing parameters for titanium. But if you go for some other materials, unknown exotic materials, there is no proper process settings. Till now, it's not available. Laser process setting is not available, and powder size is not available. Layer thickness that has to be decided. So everything does matter a lot in improving quality of the product. So this is the challenge I have additive manufacturing technology supplies. The size of the product, ease of use, and machining cost wise, there are some issues. Size of the product. You can look at the picture. These are the various additive manufacturing companies. Some companies are laser powder bed fusion. Some companies are interjetting. The Optomec is directed energy deposition size. So the next column is build size. The first one 150 mm cross 150 mm and cross 150 mm. That is the build size, build chamber size. That is the maximum size you can build. Product can be built. So that is very, very small size, isn't it? The material cost is 90,000 US dollars. You convert it into rupees. You check. And the maximum build size in this picture is 800 plus 400 plus 500. That is the maximum build size GE Additive the company is making. Okay, the cost is 250,000 US dollars. So look at the cost. The build size is more. Your cost of the product is your cost of the machine is more. So normally you have to pay larger amount of money to get a proper machine. This is one more data about maximum build size that is possible by different additive manufacturing techniques. And general information about metals is metals are very high reflective and thermal conductivities. I mean, metals with high reflectives and thermal conductivities are difficult to process by using laser additive manufacturing. Examples are aluminum and copper and gold. Metallic materials that exhibit reasonably good weldability. I mean, all the metals that are weldable are possible by additive manufacturing. And if you want to make ceramic products by using 3D printing, that is also difficult. Cracking will occur. So, more specific materials I plan to touch this only two. One is refractory metals. There are some issues with printing refractory metals. Refractory metals refers to tungsten, niobium, tantalum, rhodium, molybdenum. These are the refractory metals. Generally, conventionally, these refractory metals can be produced by powder metallurgy because of its high melting point. Tungsten melting point is more than 2000 or 3000 degrees Celsius. I don't know the exact value, but the melting point of tungsten is very, very high. Okay, you have to use powder metallurgy technique to make titanium tungsten products, refractory metal. Okay, but how to make a complex structure, how to make a desired design structure by using tungsten. So for that, you need 3D printing. But there are some issues with the processing of tungsten by using additive manufacturing. The main problems are the operating temperature. It has very high operating temperature. Of course, laser can go up to 10,000 or 40,000 degrees Celsius for a short moment. They can melt. Laser can melt tungsten powder, but that is not the main issue. The main issue is because of high thermal conductivity and high liquid viscosity and surface tension. So this is the main issue. So when tungsten is processed by using process called selective laser melting, the main issue is balling. That is the phenomenon. Balling is spacing of layers, and it is deposited. The molten liquid-like ball-like structure is deposited on the layers. So it occurs generally because of the third point. You can read. Balling generally occurs when the molten formed during laser material interaction breaks into small islands. This occurs during laser material interaction. This ball shaped liquid deposited on the surface. So when the next layer is coated on this structure, which contains balling, layer to layer adhesion may not be proper. That is a issue. That is the same issues there in magnesium also. And main issue is it is not possible to attain 100% density. Maximum attainable densities were, based on the earlier studies, were 75, 82.5, 96%. That is the maximum density attained. And the next metal, which is difficult to print, is magnesium alloys. So magnesium is almost lightweight material than aluminum. It is used for aerospace applications, biomedical applications, etc. This the picture, the chair, what you are seeing, is applied for an aircraft. Okay, it's an aircraft application. So the chair contains a lot of magnesium structures. For in the ergonomic aspect, you need to make this chair on a suitable size appropriate for a customer. So what is the problem with magnesium? It is highly reactive. First of all, it is highly reactive, catches fire very easily in powdery form. And second thing is, processing magnesium is even difficult for conventional manufacturers. It is not easy to make a product by using magnesium. You need organ ambience to make atmospheric to prevent atmospheric oxygen entering inside the furnace. And one more thing, you have to carefully control the temperatures to make a magnesium product. So melting, pouring, etc. is not an easy process for magnesium. It needs a lot of study to make a magnesium product conventional. That's the problem with magnesium. Then, if you look upon additive manufacturing, the same issues will be there. So magnesium is highly reactive. You can see the right side picture. The reactivity of various metals. Magnesium is reactive. Aluminum is reactive. Iron, copper, silver, gold. This is the order of increasing reactivity. Magnesium is reactive than aluminum, zinc, iron, copper, silver, and gold. So over the magnesium, you have calcium, lithium, sodium, and potassium. Okay, but magnesium is a lightweight material. We have to use it for certain applications. So many manufacturers try to eliminate the issue. So what they did was, during the making of powder itself, they separate minimal amount of oxygen content inside the atomization process chamber. So magnesium oxide is, so it is difficult to melt magnesium oxide. The magnesium oxide will not react that much easily. So this is they thought that this is the way to eliminate this kind of reactivity issue. Purposefully formed the magnesium oxide. But the magnesium oxide melting point is 2852 degrees Celsius. It is very difficult to melt magnesium oxide even with the laser. That is the side effects. So interlayer bonding problem is there with magnesium. Magnesium porosity problems. Porosity problems will also occur. With respect to laser parameters, porosity problem will occur. With respect to scanning speed, porosity problem occur. Crack will occur in magnesium. Even though I told a lot of difficulties, some scientists they have successfully printed magnesium metal. The picture is shown to you. This is the latest picture made up of magnesium. So I took the picture from the paper. I forgot to put the reference. Okay, South Korean journal. They have successfully printed this latest picture using magnesium metal. So same is the case with there are many problems with many different metals, not only magnesium and refractory materials such as tungsten. Nickel, there are a lot of problems. Titanium, there are a lot of issues. So you have to look on various papers to know technically what are the issues. So due to shortage of time, I restrict that slides regarding the technical issues. Some 10 slides only. The future of additive manufacturing is there are a lot of scope, functionally graded materials, different grades of materials printed at different layers, high entropy alloys, wave printing, stent, and this picture. So this picture was taken from the internet. This is a stent which is normally put inside the heart patients to expand the valves. Isn't it? So this stent is normally made by shape memory alloy, nickel titanium. Normally made by nickel titanium alloy. It's a shape memory alloy. But in this picture, the video that you are seeing, it is this material is purely titanium. It is not. It is not. It does not contain any nickel item because a shape memory alloy normally contains nickel titanium. But this material is printed only with titanium. They are testing it for the particular University of Birmingham. They are testing it for that medical applications. Pure titanium. They have constructed this stent to minimize the cost. Similarly, there are a lot of applications. This particular application is for plastic, not for metal additive manufacturing. Splint. So nano printing is also a growing field. Making a small size products, micro material products by using 3D printing. So this is lithium ion batteries, micro lithium ion batteries printed by using 3D printing. University of Illinois, they have done that. So 3D printed cars, the size is 285 micrometer size car. Vienna University of Technology, they have printed it. The foot printers, very popular field in 4D printing. 4D printing is shape memory alloy, printing of shape memory alloys. That is called 4D printing. And the 4D means the last D refers to time. Okay, 3-dimensional product we are making, and one more variable is time. With respect to time, the product shape changes. That is called 4D printing. And even though I stated many barriers, these are additional barriers. It is not covered in our topic. Lack of in-house additive manufacturing source, lack of expertise, limited repeatability, lack of formal standards, lack of proven documentation. There is no standard laws for additive manufacturing as of now. So it has to develop proper rules and regulations for printing a product. It has to be developed. I hope it will be developed. The software development capabilities, longer production timelines, limited recyclability, risk of litigation. Because if you make some product and if you sell it to the customer, if some problem arises in that product, you have to face the legal consequences, isn't it? That is called litigation. Legally, you have to face it. Warranty issues, data storage requirements, accuracy and surface finish, full color capabilities. These are other issues. The conclusion is, though additive manufacturing has been developed for the last 20-25 years, still it is a very new field in terms of getting its final shape. It's not yet developed into a full form process. It is the process is very niche. It has to go for a long way to get into the final shape, like conventional manufacturing process. But it needs support from the government as well as support from many technocrats, many industrialists, so as to boost. Encouragement is needed because today youngsters are ready to explore into the new technique. But this kind of technology support, this kind of monetary support is needed from this kind of people to get rid of this kind of challenges. So now more complex shapes and geometries are produced. As I said, the quality of the complex shaped parts, that is the main focusing area. We have to improve the complex shaped parts more. So if you compare casting and additive manufacturing, which one if you go, which of the process you will prefer? Certainly all the people, all the manufacturers will prefer casting. The reason is casting is we know casting for last 2000 years. Okay, even before independence, it is used. Before 100,000 years, it was used. Used during Greek period. So it has a long history. Casting has a long history. So many people trust that casting technique, casting and subsequent heat treatment will give the better product, high strength product. But additive manufacturing still has a long way. So that standardization should be developed. So that is the final summary. It's not conclusion, it is a summary. Thanks. So if you have any queries, you can ask.
Sir, can I have?
Yes, ma'am.
You said that rocket engines are made by 3D printing. Which material is used for 3D printing of rocket engines? Either iron or aluminum alloy. How effective they are?
Rocket engines.
Yes.
So rocket engines generally is made by inconel metal, nickel based alloy, because nickel withstand high temperature. Maybe it can withstand its properties, fatigue properties, corrosion resistant properties, etc. up to 1200 degree Celsius. Inconel metal is generally preferable for even gas turbine blades or engine material, etc.
Okay, thank you, sir.
Sir, I have a query.
Yes.
Sir, you said that this additive manufacturing for nickel and titanium is somewhat difficult.
Yes.
What is the reason, sir? What is the reason for that?
Reactivity. Titanium is reactive to oxygen. Titanium oxide is formed. So you need a close atmosphere, close ambience. At least you need a vacuum ambience or the ambience which contains argon gas. So that process will make it expensive. So if you want to print titanium, that is an expensive process because you have to spend so much of money apart from machine cost. Machine cost is crores, maybe 2 crore or 5 crore or 10 crores. So apart from that, you have to spend some money for keeping the atmospheric ambience as a vacuum environment or argon gas environment. As a titanium is highly reactive.
Thank you, sir. Thank you, Lord.
Sir, I have a question, sir.
Yes.
Sir, as you said, in powdered bed fusion, there will be a wastage of material powder, sir.
Yes.
How the partially used and the unused powders are recycled, sir?
Recycle powders. How to recycle the powders? That's the question, isn't it?
Yes, sir. Yes, sir.
So recycling of powders requires a knowledge of manufacturing of powders. First of all, we have to know about manufacturing process of powders. I am not that much aware of powder manufacturing. I studied the manufacturing process, such as gas automation, etc., etc. But recycling and all, I have to develop much more knowledge. So at present, I'm not able to answer how powder recycling will be efficient without oxygen content, etc. So you have to, you have to do some research on that.
So, okay, sir. Sir, but to reduce the wastage of powders, do they preheat the material powder, sir?
Actually, preheating the powders certainly will induce more wastages. So if you preheat temperature is very, very high. For example, if you preheat a powder to 600 or 700 degrees Celsius, you will ultimately end up in wasting more powders. Preheating means directly proportional to wastage of powders. But we can't avoid. At certain conditions, to minimize residual stress, we have to preheat the powder.
So, thank you for the answer, sir.
Sir, there are two more questions in the chat box, sir.
Yes. Significance of high entropy alloys in additive manufacturing. Now, see, so many researchers are printing. For example, in BIT Vellore, 3D printing facility is available. IIT Indore, so many people are doing research work in 3D printing. IIT Palakkad, people are doing printing work. In some private agencies, such as Wipro 3D, they are printing. And RRKit, you type it in Google, RRKit, Raja Ramana Center for Advanced Technologies, it is in Indore, they are printing. So many people are now researching about high entropy alloys. High entropy alloys is normally we use 2 or 3 materials. We mix it together and we use powder manufacturing technique or some other casting technique. We make an alloy, isn't it? We make an alloy product, Ti64, etc. It's an alloy. Ti64 contains only titanium, vanadium, and aluminium. So this is an alloy. And 4 or 5. Suppose if an alloy contains more than 10 combination, aluminum, copper, vanadium, tungsten, silicon, magnesium, manganese. If you put all together in small percentage, that is called high entropy alloys. And different combinations, many materials. That is called high entropy alloys. So what is the significant parameter of in powder bed fusion process? What is the significant parameter in powder bed fusion? Obviously, laser intensity and laser scan speed. That has close relevance. That influences the powder strength. Your scan speed, how much speed the laser is moving, and what is the energy you are supplying to melt the powder. These two are very, very dominant.
Participants, do you have any other questions?
Sir, good afternoon, sir.
Yes.
So I have 2 questions, sir.
Yes.
Sir, I'm talking about metal powder, sir. Actually, the SS316L powder is there, no, sir. The composition, does it vary, sir? I have seen in some papers that the composition it is different. So what is the reason behind that, sir?
So same material name, but the composition is different.
Yeah. For example, the chemical composition is different. So what is the reason behind that, sir?
See, the powders are manufactured by a single company. All the companies have R&D. All the companies have R&D. So slightly they make some changes, but the changes may not be drastic.
Okay.
That will be
okay. That's what there is
negligible.
a little bit
That is
changes
negligible.
only. Okay, sir. And one more question, sir. That is the reuse of that powder. How much effect will be on the properties, sir? For example, I'm using a fresh powder for manufactured component. So after doing some testing, we will be getting some value. After that, if you reuse that powder and when you're preparing the tensile test like that we're doing, how much effect will be there, sir? Any
So, as I said,
idea on that, sir?
for reusing the powder, there is nothing wrong with reusing the powder. You can reuse the powder once or twice or thrice or 5 times. That is okay. But if you use it again and again for 10 or 20 times, what will happen? This powder is normally already it acquire oxygen from the atmosphere. It is kept in the atmosphere for so long time. It is not kept in a proper ambience. Okay, we are reusing. We are taking it again. We are putting it in the powder bed. So for doing this process again and again, repetitive in nature, so it will capture lot of atmospheric gases, lot of atmospheric oxygen.
Yes, sir.
So if oxygen mixes with the powder, what will happen? The strength, it will affect the strength. The final end product.
Yeah, that's what I'm
may not
asking.
get-
Approximately, what will be the percentage? For example, some 20% there will be difference in the strength like that. Any idea on that?
It depends upon the oxygen content. We can't state the exact value. It depends upon how much
Okay,
oxygen
sir.
that powder acquired. At present, I don't have that data.
Yeah, it's okay. Sir. Okay, thank you, sir. Thank you.
Thank you.
Any other queries?
Sir,
Yes.
sir, as you said, powder bed fusion is a slow process, sir. So how effectively it is used in mass production, sir?
So mass production, if you look into it, you have to use a direct energy deposition. That is the best way. Direct energy deposition is the best way to produce a product in massive way, but you can't get the accuracy. But powder bed fusion is suitable for making small size products, metal products with a limited quantity. But at present, some manufacturers, they have increased the build rate. Foreign manufacturers, not in India, because in India, I believe that no company is manufacturing metal powder additive manufacturing machines. Some EOS, GmbH, Stratus is